Stand in the room you're in right now. You can see the walls, the floor, the objects around you. But almost everything here, about 95% of it, is completely invisible. Not hidden, not transparent, invisible by the laws of the universe. And this isn't imagination, it's reality. In 1933, astronomer Fritz Zwicky looked at a distant cluster of galaxies and realized something was terribly wrong. The galaxies were moving so fast they should have flown apart long ago. But they didn't. Something unseen was holding them together. He called it dark matter. Today we know that everything we've ever touched, seen, or been made of accounts for less than 5% of the universe. The rest is something we cannot see and barely understand. What if the universe you know is just the surface of something far larger? This is where the mystery begins. Let me take you back to 1970. Vera Rubin, an astronomer at the Carnegie Institution, was doing something that seemed routine at the time. She was measuring how fast stars orbit around the center of galaxies. It was the astronomical equivalent of checking your watch. Standard, predictable, except what she found wasn't predictable at all. Understanding what Rubin discovered requires understanding how galaxies should work. Think about our solar system. Mercury races around the sun at 47 kilometers per second. Earth moves at 30 kilometers per second. Neptune, way out in the distant cold, crawls along at just 5 kilometers per second. The farther you get from the sun, the slower you orbit. This is fundamental physics. This is Newton's laws in action. This is how gravity works. Galaxies should follow the same rules. The visible mass of a galaxy, all those billions of stars, concentrates toward the center. So stars at the edge should orbit slowly, just like Neptune. The rotation curve, the graph showing orbital speed versus distance from center, should rise near the core, then drop off dramatically toward the edges. But when Rubin measured the Andromeda galaxy, she found something extraordinary. Stars at the edge were moving just as fast as stars near the center. It was as if Neptune was orbiting at the same speed as Mercury, as if gravity itself was breaking its own rules. She checked her calculations. She recalibrated her instruments. She observed galaxy after galaxy after galaxy. The result was always the same. The rotation curves weren't dropping. They were flat. Flat rotation curves mean only one thing. There's more mass in galaxies than we can see. A lot more mass, spread throughout the entire galaxy like an invisible scaffold. The visible matter, all those stars burning across the cosmos, represents maybe 10% of the mass needed to explain what Rubin observed. The other 90% of each galaxy is made of something else entirely. Something that doesn't emit light, something that doesn't reflect light, something that doesn't interact with light at all. But here's what makes this truly unsettling. Dark matter isn't just in galaxies, it's everywhere. When astronomers calculated the mass needed to hold galaxy clusters together, they found the same problem Zwicky had discovered decades earlier. Galaxy clusters contain thousands of galaxies, each containing billions of stars. But even all those stars, plus all the gas and dust between them, plus all the black holes lurking in galactic cores, account for only about 15% of the mass required by gravitational calculations. The rest is phantom mass, invisible, undetectable by any telescope humanity has ever built. Think about what this means. When you look at a galaxy cluster through the most powerful telescope on Earth, you're seeing less than 1/6 of what's actually there. The rest exists in a form we cannot observe, cannot touch, cannot directly measure. We know it's there only by its gravitational fingerprint, like a detective inferring an invisible man by the footprints he leaves in snow. Scientists initially hoped dark matter might be ordinary matter we just couldn't see. Maybe it's brown dwarfs, failed stars too dim to detect. Maybe it's rogue planets drifting between galaxies. Maybe it's primordial black holes formed in the early universe. These objects, collectively called machos, massive compact halo objects, could theoretically account for the missing mass without requiring exotic physics. For a decade, astronomers searched. They conducted surveys looking for machos through gravitational microlensing, the brief brightening of a background star as a massive object passes in front of it. They found some, but nowhere near enough. Machos might account for perhaps 2% of dark matter at most. The missing mass isn't ordinary matter hidden in darkness. It's something fundamentally different, something that passes through normal matter like light through glass, something that has never been directly detected in any laboratory on Earth. But the evidence forces us to confront an uncomfortable possibility. We live in a phantom universe, where everything we've ever known is merely the visible decoration on an invisible foundation. And that foundation is about to reveal properties stranger than anyone imagined. If dark matter exists, it should leave signatures beyond flat rotation curves. It should shape the universe at every scale, and that's exactly what scientists discovered. In 2006, astronomers observed a collision between two galaxy clusters in a system called the Bullet Cluster, located 3.7 billion light-years from Earth. When galaxy clusters collide, it's the most energetic event in the universe since the Big Bang. But something strange happened during this collision. The visible matter, mostly hot gas that glows in X-rays, slammed into itself and slowed down just as you'd expect. Basic physics. Two clouds of gas colliding behave like two cars crashing. They crumple, they slow, they pile up. But the gravitational center of each cluster, measured through gravitational lensing, the bending of light from background galaxies, didn't slow down. The gravity kept moving as if nothing had happened. The mass and the light had separated. For the first time in history, astronomers watched dark matter and ordinary matter diverge. The implications are staggering. This observation tells us dark matter isn't just invisible, it barely interacts with anything at all. While normal matter collided and heated up, dark matter passed through itself like ghosts walking through walls. The two halos of dark matter, each containing trillions of solar masses, interpenetrated and emerged on opposite sides with barely any interaction. This rules out almost every alternative theory of gravity. If dark matter is just a misunderstanding of gravitational physics, then mass and gravity can't separate. But in the Bullet Cluster, they did. You can literally see the ordinary matter in one location and measure the gravitational force in a completely different location. Scientists discovered similar separations in other colliding systems. The Musket Ball Cluster, Abell 520, Abell 2744. Each one reinforced the same message. Dark matter is real, it's everywhere, and it's fundamentally different from everything we've ever encountered. But perhaps the most compelling evidence comes from the early universe itself. In 2003, NASA's Wilkinson Microwave Anisotropy Probe, WMAP, mapped the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation formed 380,000 years after the universe began, when the cosmos cooled enough for light to travel freely for the first time. The pattern of temperature fluctuations in this radiation is like a baby picture of the universe, showing the distribution of matter when everything was young. Scientists can analyze these patterns like archaeologists reading ancient texts. The size and shape of the temperature fluctuations encode information about the composition of the early universe with extraordinary precision. The data revealed something remarkable. Ordinary matter made up exactly 4.9% of the universe's total energy density. Dark matter constituted 26.8%. The rest, 68.3%, was something even stranger called dark energy, but that's another story entirely. These numbers aren't rough estimates. They're measured to better than 1% precision. The cosmic microwave background provides an independent confirmation of dark matter that has nothing to do with galaxy rotation curves or cluster dynamics. The early universe needed dark matter to explain patterns in radiation that formed 13.8 billion years ago. But this represents just one piece of a much larger puzzle hidden in the structure of the cosmos itself. As cosmologists built computer simulations of cosmic evolution, they discovered something unexpected. If you simulate the universe with only ordinary matter, you don't get the universe we observe. Galaxies form too late. Cosmic structure is too smooth. The distribution of matter is fundamentally wrong, but add dark matter to the simulation, and suddenly the universe comes alive. Dark matter began clumping under its own gravity long before ordinary matter could. In the early universe, ordinary matter was too hot, too energetic. Radiation pressure kept it spread out like steam in a boiler, but dark matter, unaffected by radiation, started forming structure immediately. These dark matter clumps became gravitational wells. Ordinary matter fell into them like water draining into a sink. The largest dark matter concentrations became the centers of galaxy clusters. Medium concentrations became galaxies. Smaller concentrations became the seeds for dwarf galaxies. Every galaxy exists because of dark matter. Not alongside it, not supported by it, because of it. The visible universe is like frost forming on a spider web. The web itself, the dark matter, is invisible. But without the web, the frost would have nowhere to form. It would scatter randomly, never coalescing into the intricate patterns we observe. Computer simulations show this with stunning clarity. When researchers at the University of California and the Max Planck Institute ran simulations of cosmic evolution, they produced a structure they call the cosmic web, a vast network of dark matter filaments spanning the observable universe. Galaxy clusters form where filaments intersect. Galaxies line up along the filaments like beads on a string. Between the filaments lie cosmic voids, vast empty regions containing almost nothing. This predicted structure matches observations with eerie precision. When astronomers map the positions of millions of galaxies using surveys like the Sloan Digital Sky Survey, they see exactly this pattern. The cosmic web isn't just a simulation artifact. It's real. It's the fundamental architecture of the universe. But the most remarkable discovery involves what dark matter is doing right now in this galaxy, around this solar system, around you. According to calculations, Earth is swimming through a dark matter wind. As our solar system orbits the galactic center at 220 kilometers per second, we're moving through a dark matter halo like a submarine moving through water. Approximately 3 trillion particles of dark matter pass through your body every second. You can't feel them. They don't interact with your atoms through any force except gravity, which at the scale of individual particles is vanishingly weak. They're ghosts passing through you at relativistic speeds, leaving no trace, no mark, no evidence of their passage. And yet, their collective gravitational influence holds our galaxy together. The Milky Way contains approximately 1 trillion solar masses of dark matter, compared to about 60 billion solar masses of visible matter. We're living inside a dark matter halo that extends far beyond the visible disk of stars. The evidence extends beyond mere existence into the realm of cosmic engineering. Dark matter doesn't just exist passively. It sculpts reality at every scale, from the formation of the first stars to the ultimate fate of galaxies billions of years in the future. So what is dark matter made of? This is where the mystery deepens into something truly strange. After decades of research, scientists still don't know, but they have theories, extraordinary theories. The leading candidate is something called a WIMP, a weakly interacting massive particle. These hypothetical particles would have mass somewhere between 10 and 1,000 times the mass of a proton, and they would interact through gravity and possibly through the weak nuclear force, the same force responsible for radioactive decay. WIMPs are an elegant solution. If they exist, they would have been produced in enormous quantities during the Big Bang. As the universe expanded and cooled, WIMPs would have naturally settled into exactly the abundance we observe today. Physicists call this the WIMP miracle, the stunning coincidence that particles with these properties would automatically produce the right amount of dark matter. But here's what makes this truly fascinating. If WIMPs exist, they should occasionally collide with ordinary matter. Not often, maybe once per kilogram of detector material per year, but occasionally. And when they do, they should produce a tiny flash of energy that sensitive detectors could observe. Physicists have built detectors specifically to catch these rare collisions. The Large Underground Xenon Experiment, LUX, used 370 kilograms of liquid xenon, cooled to 100 degrees Celsius, shielded a mile underground to block cosmic rays. The Xenon 1T detector in Italy used even more, 3.2 tons of ultra-pure xenon. The Pandex experiment in China took the same approach in an underground laboratory 2,400 meters below the surface. After decades of searching, these experiments have detected nothing, not a single confirmed WIMP interaction. This represents one of the most profound null results in modern physics. Either WIMPs don't exist, or they interact even more weakly than predicted, or we're looking in the wrong way entirely. But WIMPs aren't the only possibility. Alternative theories propose axions, extremely light particles first hypothesized to solve a different problem in particle physics. If axions exist, they would be produced not through mass but through quantum field oscillations, forming an invisible fluid permeating the universe. Experiments like ADMX, Axion Dark Matter Experiment, are searching for these particles using powerful magnets and ultra-sensitive radio receivers. Other theories get even stranger. Primordial black holes formed in the first fraction of a second after the Big Bang. Sterile neutrinos that barely interact with anything. Dark photons that mirror ordinary photons but remain invisible. Self-interacting dark matter that creates dark forces analogous to electromagnetism, possibly even forming dark atoms, dark molecules, dark chemistry in a shadow realm overlapping our own. This forces us to reconsider fundamental assumptions about what constitutes reality. We may be living in a universe where the matter we're made of is the exception, not the rule, where the fundamental building blocks are particles we cannot directly observe. The search for dark matter has become one of the most intensive efforts in modern science. The European Space Agency's Euclid telescope, launched in 2023, is creating the most detailed 3D map of dark matter ever attempted by observing how its gravity distorts light from billions of galaxies. NASA's Nancy Grace Roman Space Telescope, scheduled for the mid-2020s, will perform similar observations with even greater precision. On the ground, the Vera C. Rubin Observatory in Chile, with its 8.4-meter mirror and 3.2 gigapixel camera, began operations in 2024. It will photograph the entire visible sky every few nights for 10 years, creating a movie of the universe that will reveal dark matter's gravitational effects in unprecedented detail. But perhaps the most intriguing searches are happening underground and in space, looking for the particles themselves. The Super CDMS experiment at SNOLAB in Canada is searching for dark matter particles lighter than previously explored, using germanium and silicon crystals cooled to just 0.015 degrees above absolute zero. The CRESSD experiment in Italy uses calcium tungstate crystals to search for even lighter candidates. The DARWAN detector, under development, will use 50 tons of liquid xenon, the largest dark matter detector ever conceived. In space, the Alpha Magnetic Spectrometer on the International Space Station has been measuring cosmic rays since 2011, looking for signals of dark matter particles annihilating each other. When two dark matter particles collide, they should produce a flash of ordinary particles, positrons, antiprotons, gamma rays. The AMS has detected excess positrons at certain energies that might represent dark matter annihilation, or might not. The signal remains ambiguous. Recent breakthroughs suggest we may be approaching the problem from too narrow a perspective. In 2023, researchers proposed that dark matter might not be made of particles at all. Some theories suggest it could be topological defects in spacetime itself, cracks in the fabric of reality left over from phase transitions in the early universe. Others propose dark matter emerges from modifications to gravity that only become apparent at galactic scales. The LIGO gravitational wave detector, which famously detected merging black holes, is now being used to search for ultralight dark matter. If such particles exist, they would create oscillations in the fundamental constants of nature, tiny ripples in the strength of gravity itself, that LIGO's exquisitely sensitive instruments might detect. What becomes clear is that dark matter isn't just a missing piece of the cosmic puzzle. It's a window into physics beyond the standard model, beyond everything we've confirmed in particle accelerators. Discovering its nature won't just solve one mystery. It will open entirely new branches of physics, new understandings of how reality works at its most fundamental level. The implications extend beyond pure science. Understanding dark matter might reveal new fundamental forces, new forms of energy, new principles that could revolutionize technology in ways we can't currently imagine. Every major discovery in physics has led to technological transformation. Quantum mechanics gave us computers and lasers. Relativity gave us GPS and nuclear power. What will dark matter give us? We stand at the threshold of potentially the most important discovery in physics since the quantum revolution, and the evidence is pointing toward answers that grow stranger with each passing year. Now we arrive at the deepest implications, the questions that keep physicists awake at night. If dark matter is real, and if it makes up 85% of all matter in the universe, then what does that mean for our understanding of reality? Consider this: you are made of ordinary matter, protons, neutrons, electrons, the standard particles of the standard model. Everything you've ever touched, everything you've ever seen, every atom in every star in every galaxy we can observe is made of the same stuff. But that stuff represents less than 5% of the universe. The most profound implications emerge when we consider what this means for existence itself. We're not just rare. We're fundamentally different from the overwhelming majority of matter in the cosmos. We're the exception in a universe dominated by something else entirely. What if dark matter isn't alone? What if there's an entire dark sector, a parallel universe of dark particles interacting through dark forces, existing in the same space as our universe, but remaining forever invisible? Some theories propose exactly this. If dark matter self-interacts, it could form structures, dark atoms, dark molecules, dark chemistry, dark stars that shine with dark photons we can never see, dark planets orbiting those dark stars, and perhaps, though this is pure speculation, dark life. A shadow biosphere exists alongside ours, made of particles that pass through us like we're empty space, living in worlds we can never observe, evolving under laws of dark chemistry we can never directly study. This sounds like science fiction, but the evidence forces us to consider possibilities that seem impossible. We already know dark matter exists. We already know it has complex behavior. The question is, how complex does it get? There's another possibility that's somehow even stranger. What if dark matter is actually ordinary matter from parallel universes bleeding through into ours? Some interpretations of quantum mechanics suggest the universe constantly splits into parallel branches. In one branch, you made breakfast this morning. In another, you didn't. Every quantum event creates a fork in reality, generating an infinite multiverse of parallel timelines. Normally, these universes never interact. But gravity, according to general relativity, curves spacetime itself. And if spacetime is shared between parallel universes, then gravity could leak through. The dark matter we observe might be the gravitational influence of matter in parallel realities, pulling on our universe from dimensions we can't access. This remains highly speculative, but it's consistent with the evidence. And it would mean dark matter isn't mysterious particles in our universe. It's normal matter in other universes, pressing against ours through the membrane of spacetime. Perhaps the most disturbing question is this: if we can't see 95% of the universe, what else might we be missing? Dark matter and dark energy together constitute 95% of everything. But these are categories defined by absence, by what we can't see, can't measure, can't understand. They're placeholder names for our ignorance. What if there are other components we haven't even detected yet? Other forms of matter or energy that leave no gravitational signature? Entire categories of reality that remain invisible not because they don't interact with light, but because they don't interact with anything we can measure. We pride ourselves on understanding the universe. We've mapped the cosmos, decoded the atom, and revealed the quantum realm. But if 95% of reality is invisible to us, how much are we really seeing? How much are we missing? The universe might be far larger, far stranger, far more complex than anything we've imagined. Dark matter is just the first hint, the first crack in our understanding, the first sign that reality extends far beyond the narrow band of existence we call normal matter. We began this journey with a simple observation: galaxies rotate in ways they shouldn't. Stars move too fast. Clusters hold together too tightly. The universe doesn't behave the way our physics predicts. We've followed the evidence through galactic halos and colliding clusters, through cosmic microwave background radiation and computer simulations, through underground laboratories and space telescopes. Every piece of evidence points toward the same conclusion. We live in a phantom universe, where everything visible is just scaffolding on an invisible foundation. Dark matter is real. The scientific consensus is overwhelming. Dozens of independent observations, using completely different methods, all lead to the same conclusion. The question is no longer whether dark matter exists. The question is, what is it? We may be on the verge of finding out. The next generation of detectors, telescopes, and experiments may finally reveal dark matter's nature, or they may deepen the mystery, revealing that dark matter is even stranger than we thought. But whatever we discover, the implications will transform our understanding of reality, because dark matter isn't just about explaining galaxy rotation curves. It's about understanding what the universe is fundamentally made of. It's about recognizing that everything we've learned in centuries of science applies to less than 5% of existence. The visible universe, all the stars, all the galaxies, all the matter we're made of, is foam on an invisible ocean. And we're just beginning to develop tools to measure the depths beneath. The universe is vast. The mysteries are endless. The journey continues. But one thing is certain: we don't live in the universe we thought we did. We live in a phantom realm, surrounded by invisible matter, governed by forces we don't understand. And somewhere in that darkness, hidden in those phantom galaxies, lies the key to understanding everything.